Hello, good evening, everyone. Am I audible?
Yes, sir.
Okay, then. Today we are going to discuss week 8 PPA problems. Okay, first of all, let me share my screen. Yes, is my screen visible? Can anyone respond, please? Is my
Yeah,
screen
yes,
visible?
signal visible.
Okay, then let us move to today's questions. This is the second question. And in this week, and week 8, we have two PPA problems. And here is the first question. Sir, Atul sir,
Yes.
sir, I have this issue about this screen compatibility. This issue, sir.
Okay. So I think the test cases are big for this. Oh, this issue is not resolved, I think, till now.
Oh,
Can you check the test case? What is the length? Okay, so this test case, no, actually, this is vague.
yes.
Okay, I'll ask to the operational team. They will figure out this.
Oh, okay, sir. Okay, let me start the session. And here is the first question for this today's session. And we have to write a Python function, kth largest, and an array, and the kth position is given as a parameter, a list of arrays and a size of n, and an integer k, such that k less than or equals to n, and returns the kth largest integer in an array. The solution should run in order of n time. So it is given that the solution should be in order of n time. Can anyone have any idea regarding this? How to find the kth largest element in an array? Any Navi approach or brute force approach that you have in your mind? Can anyone respond? Do you have any ideas how to find the kth largest element in an array? Given an array, we can directly know that in this array we can directly say that
We
if you
can
want to find the
we can
second
sort the array. We can sort the array and take the value from the position k
yes, we can sort the array
in
and we
naive
can take the
approach.
position. Yes, in a approach. If you sort it, if you want the kth largest element, and if I sort the array given array into the in descending order, and what position should we return? Do you get that?
Kth position.
Yes, kth position.
Yeah.
Actually, the indexing starts from the 0, right? So we should return the k minus 1th position if we sort it in the descending order. If we sort the elements in
Yeah.
descending
Okay.
order,
Kth
if
element, I mean. Kth element.
yeah,
Okay.
kth element, okay. And
Oh,
is
yeah.
there any other approaches do
Sir, I
you?
have a question. I have a question here. If at all the array contains duplicate elements,
Yes.
so do we consider the duplication also?
So
Like
your question
if
is
the array is like 5 comma 10 comma 10, if that is the array, then
okay,
second
5 comma
largest
5.
element will be 5
Yes,
comma
5
10
is
comma
a
10.
yeah. In this we
5
can say
10
this
10.
5 is the second largest element, right?
No, no, I'm asking 5 10 10.
5, 10, 10.
Yeah. In this,
So
the
in this
second largest
question,
element is 5, right?
so here in our question, it is not mentioned about these duplicates, right?
Yes, but this
So
is my general query. There's nothing specific mentioned whether to ignore or whether to consider. So I'm asking this.
so let us try to run this by giving some duplicate inputs and let us check whether it gives the right output or different output. Okay.
Okay, okay.
Later we try to do all possible by giving all possible inputs and let us check so that everyone could have the doubt cleared. Okay. Okay, then first of all, I want to explain different methods. What are the different methods we are able to solve this problem. Okay, and the first method for this okay, the question is to find the kth largest element. Okay, and first of all, let us move to the first approach. And here is the first approach. We can given an array, okay, and in an array we can traverse this in Python. What is the simple in Python? What is simple means we can remove the largest element, right? We can easily find the maximum value by using this max function, and we can remove this maximum value by using the remove function, right? You all know these functions.
Yes, sir.
Can anyone respond? So what we can do is we can traverse this array up to kth position, k minus 1th position. So while traversing up to this k minus 1th position in this array, we can find the maximum. Okay, we can find the maximum from the array, and we can remove this maximum, right? So by continuously removing the k minus 1 maximum values, so finally we can return the kth maximum, right? After completion of this for loop, it will iterate k minus 1 times, so that let us take an example. If we have an example 1 2 3 4 5, okay, this if this is an array, let me take here 6. If this is an array, if you find what is the maximum value from this array, if I want to find the k is equal third maximum, okay, so what is the first maximum here in this array? 6 is the first maximum, right? So if so the third, we need to find the third maximum. So we iterate this array k minus 1 times. That means 2 times. So the first maximum is 6. If we remove this 6, then for the next iteration, what is the maximum value from this array? No,
5.
if 5 is the maximum array. So later we remove this 5 also, and this we will be exiting from this for loop, right? The k minus 1 iterations are completed, and later we are going to return this maximum of this array, right? Later, what is the maximum? 4 is the maximum, so it is a third maximum from this array, right? Hope you understand the logic, the first approach.
Sir, after exiting, how are you finding that 4 is a max?
We have direct function, right? Max function. So if you apply this max function on this array, it will directly return us the maximum value from this array, right?
Yes, I got that now.
If
You're
you
removing the
don't
one
want,
before that.
yes,
Before the kth element, we're removing all the elements before the kth element.
yes. Our aim is to find the kth largest element, but we are going to traverse only up to k minus 1, so that we can remove this k minus 1 large elements and we can return the kth largest, right? We are going to remove this 1 to k minus 1 largest elements, and for returning this, we are not traversing until this point, right? So we can traverse up to k minus 1, and we can remove these maximums, and later we can return the kth largest value here. So what is for this, the time complexity takes me, okay, let me write this pseudocode properly so that it will be convenient for us to discuss about the time complexities. Okay.
So can this board be made white?
Okay, you need this board white. Okay. Remove these lines. Okay.
Yes, sir.
Okay, let me remove this also. Okay, our first approach. Now, in our first method, what we are going to do, given an array, this is a list of an array, and we are going to traverse, and the kth, we need to find the kth largest element. So we are going to traverse for I in array, and we are going to traverse up to k minus 1 element, right? And in this, we are going to remove the maximum values until k minus 1 element, and later, after completion of this for loop, we are going to return the maximum of this array. So it will become the kth maximum. So can anyone tell me what is the time complexity this pseudocode is taking?
Order of n.
Order of n square. N square.
How can you say? Yes, it is not n square. Here it is traversing up to till only k, right? So it is k into
Yeah,
n.
but K will automatically approach N, right?
So we might not know, right? K might be n or k might be a constant value. So in worst case, if k is n, it will be n square, right? So if k is a constant, it will be only n, order of n. It is the best for best case, but we don't know what is the k value, right?
Yeah, in
We are going
worst
to,
case, it will approach order of N square.
yes, because we are going to find, instead of traversing this k times, we can directly return, right? We can directly find the minimum. So in a, if in a array 1, 2, 3, 4, 5, and here are 5 elements. If I want to find the fifth largest element, so what is the fifth largest element? It is the first minimum element, right? So instead of finding the fifth largest element, we can find the first minimum element, or the smallest element, the first smallest element. So it will be the fifth largest element. So we can check a condition. We can check with the size of the array. We can check with the, what is the size of this array? It is 5, right? And if you want to find the fifth largest, if you remove this 5 from 5, we will get 0, right? So instead of finding the largest element, if you approach this minimum, if you want to find, if you are go for the smallest element, it will be easy, right? We can complete this function within a few number of steps, right? Did you get
Yes.
this?
Yes, sir.
So try to build your code in such a way that it will take only few number of steps, so that the code will be executed sooner. So by writing this code like this, it will take k into n, or order of kn. In worst case, it might go up to n square. In the best case, it might be order of n, right? We can't say it is order of n unless whether the k is constant like 1, 2, 3 until these values. We don't know that. We don't know the array limit, array size, right? It might be having 1,000 elements or 100 elements. So it will take kn time. It is the average time, average case. Okay. So let us move to the second approach. And in our question, what is it? What we can see, it is mentioned that we have to find the kth largest element in order of n time, right?
Rafael. Yes, sir.
Okay, let us move for the second approach. Okay, then. Okay, in the approach two, we can sort the array and we can directly return this index, right? So given an array,
Yes, yes.
sorry, 1, 5, 4, 3, 2. So this is an array, and our aim is to find the second largest element. So to find the second largest element, we can directly sort this array and we can directly return the index, right? So by sorting this array, what are the values we get? If we sort this array in this ascending order, we will be getting 1, 2, 3, 4, 5. Then we can directly return the index, right? We can directly return what is the value? What
-2.
should we pass? Yes, as we are oh yes, we can directly return -2, or we can return the length of the array.
Length of the array minus that, which, yeah.
Yes.
Right, we can directly return like this, or in Python we also have this minus negative indexing, right? So we can like return like this. Or if we sort this array in descending order, we will be getting these elements. So we can directly return the maximum element, which is at the k minus 1th index, right?
Yes. Another one index.
Yes, we can.
So these are two approaches. And what is the time complexity we get by going this approach? This approach to, we will be
Test will
getting
be
order of
order of
log
n
n,
log n.
n log n, right? Actually, we are sorting this.
Yes.
So sorting takes order of n log n. And this, for returning this index, it is taking order of 1, which is a constant time. So we neglect this constant time. And n log n is the time complexity, which is taken by this approach. Either we take the ascending order or descending order, it will take n log n time, right? So let us move to the third approach, which we can solve this problem. And in this third approach, we can take this priority queue, right? Or we can say we can build this using this heaps.
Heap sort. Heap sort.
Similar to this kth largest to find the kth largest, or it might be given that to find the kth smallest. Any of this question. If our aim is to find this kth largest or kth smallest, we can build a heap and we can directly extract the minimums, right? Hope you all know this concept
Yes.
of heaps, right?
Yes, sir.
So if we have some elements in here, if you are trying to build a max heap, right? Max heap. So let me explain you about this max heap. And in our max heap, how will be the elements stored in this array? The elements will be stored in a descending order, right?
Yes, sir.
Are you able to get this? In a
Yes.
max heap, the elements will be stored in the descending order. For example, let us say 8, 7, 5, 4, 3. So these are the elements which are present in this max heap. So to return the third largest element, okay. For returning this third largest element, and how this
But it can be 8
this
by 7 also, right, in the heap. It is not
yes
guaranteed that the array representation will be in the descending order. Only the two child nodes of the parent node will be smaller than the
yes,
uh,
and yes, but if we
But the
traverse
root
this
node will always be the maximum.
maximum, yes, if we traverse this,
yeah.
we will be getting this descending order, right? By traversing this max heap.
We cannot, right? We cannot assure it, right? What if the
Yet
root node is 8 and the left child is 5 and the right child is 7? We get 8, 5, 7, right?
No, every time we remove from the root, we will balance it.
yes,
In this only we are
Yeah,
considering the case, right?
just
We
by
only
traversing we can cannot get, but
no,
again
no,
by
no, that is
balancing
not
the
the
heap.
point. Here only the kth element. Na? So for that we will only see the root one. Every time the
here
root is removed,
is
others
the
are
tree will
balanced.
be like this, right?
It will be balanced. So again the highest one will come to the top.
So here is a
Okay, you are
max heap
removing.
which
I
we
thought
have
you are
built.
just
So
traversing and building the array and accessing the element.
No,
Okay,
no,
if you're
it is
removing,
like
that's fine.
for
the removal of the maximum case, the first one. Exactly this is.
Yeah, that is fine. If we
so we
pop
are
the maximum
we are going to
element.
remove. Yes, we are going to pop this until k time, right? K times. Then while we are going to pop this k, we are going to return that element, right? To finding the kth largest element. So in this we are going to find the third largest. So first of all we are going to pop this first one, and after popping this we are going to replace this with the last node, and we are going to heapify this. And after heapifying this, what are the elements we are going to get? We are going to get this tree, right? We are going to get this heap. Hope you understand this. After removing this, we are going to replace this with the last node, and after replacing this with the last node, we are going to heapify this, and then the heap will be looking like this, right?
Yes, sir.
So we have popped this one time, and the
Yes.
second time if we pop this, and later we are again going to replace this with the leaf node, which is 3, and we are going to apply the heapify. What will the elements be? Okay, after applying heapify, we will be getting
Five and the root
here
node.
3, 4, and 5. After applying heapifying, these are the elements which are present in this, right?
Yes, sir.
So for the third time, while we are going to pop this, we are going to return this as a kth largest element, which is the third largest element, right? So while we are popping the final time, kth time, we are going to return this as an answer solution. Okay. By this approach, we can also go this. We can also do this problem in this approach. Okay, using these heaps. Hope you understand how to do this solve this problem using heaps.
Sir, it will take log and time, na?
Yes.
Let me explain you the time
K and
complexity. It
login.
does. So for building heap, it will take order of n, right? We need to the given input is in the form of an array, so we need to build a heap, right? For building heap, it will take order of n, and to find the kth largest element, for one popping, it will take log n, right?
Yes,
For
sir.
one removal, it will
Yeah,
take log n. So
yes.
we are going to check until kth largest element, right?
K log.
So so the time complexity will be for it is for building plus k log n for popping. So this is the time
Okay.
complexity which will be taken by using this heaps. Okay. Are you getting it?
Yes,
Yes,
sir.
sir.
Okay, then. And the final approach we can solve this in the okay. Let me. And the last approach, and the most optimal approach is we can use the quick selection approach. Okay, and this quick selection approach is similar to this quick sort algorithm. Okay, in quick sort we are doing this partition stuff, right? Hope you all remember this partition. How we do this partition? We are going to do this partition, and we are going to get the pivot index, right? To get the pivot
Yes,
index, we
sir.
are going to do the partition, and we'll be getting this. So in this quick selection approach, we are going to use the same partition algorithm, and we are going to find the kth largest element. So most of the approach is similar to this quicksort approach, but only thing is in quicksort, what we are going to do, we are going to do, if this is an array, if this is a pivot element which we got, we are going to again do the same approach on both the left side and right side, right? We are going to again do the same partition approach on both left side and right side in quicksort. We get this?
Yes, sir.
Yes, sir.
But coming to this quick selection
Here we
approach,
will check only one
if an array,
side.
only one side we are going to do. Okay, in, in quick selection approach, our aim is to find the kth largest element. So if there are n elements, if the kth element is present here, so we are going to find the pivot element, and if this is a pivot element, this is the right side, and this is the left side. So every time we are going to check the kth element with the pivot index. Okay, the kth index with the pivot index. So if the kth index is equals to this pivot index, so we are going to return as it is the kth largest element. Okay, so if it is kth index, k is greater than this pivot index, so what is the case at which side the elements will be at
Like a
which side
binary.
the elements will be? Yes,
It's like a binary sort after that, right?
yes, like similar to that, but we cannot assure that the elements will be equal on both sides, right? As we are using this quick selection approach, in quicksort we don't know which will be the private element and at which part we are going to partition. It might there will be some situations where only one element will be on one side and the rest of the elements will be on the next side, right?
Yes, sir.
So it is like median approach. Okay, we are every time we are going to find the middle value and we are going to check like that approach, median of medians. Okay, similar to that.
Yes, sir.
So if the kth largest is present on the right side, we are going to do the stuff on right side. Okay, only on the right side, and we are going to take a pivot element, and later we are going to do the same stuff on that. So if like that, we continuously do this to find the kth largest element. Okay, let us
So
take an
I've
example.
implemented the same. Yeah, I've
Okay,
implemented the same approach. The public test cases are passing, and out of 5 private test cases, only 3 are passing. So I am not sure what's going wrong.
okay, okay. After completion of this, let us discuss about that.
Yes,
Okay,
sure. Okay, sure.
let us analyze your code also later. What are the mistakes are there in your code? Okay, okay. Let me take an example. 1, 3, 2, 4, and 8, and 5. So let us explain by taking an example. So we can take the pivot element either the first element or the last element, we can also take the random element, right? By using this random function, randint, we can take the random element from this given array. Okay. So in this, I'm going to take the last element, which is 5 as a last index, which is 5 as a pivot element, and by instead of taking this last element, if we take this random, what is the advantage? Can anyone answer?
Which one, sir, instead of 5?
Instead of taking the first index or the last index as a pivot element, if we take the random element from this array, what is the advantage that we are going to get?
we can avoid the
While we
worst
are-
case scenario where all the elements fall on one side.
Yes, yes, absolutely. We can avoid this worst case scenario, right? So that but by taking this random, the best case and the worst case will be n log n. Okay, in sorting, in case of sorting. Okay, but we can use this approach in this problem also. You can take the random for taking the pivot element, but for this explanation sake, I'm going to take this last index as a pivot index. And let us start our tracing. Let us first of all let us initialize this I to minus one index. These are the indexes 0, 1, 2, 3, 4, 5. Let me take them clearly. Open 3, 2, 4. These are the elements, and the indexing is 0, 1, 2, 3, 4, 5. And this is the pivot element. And the ith index will be pointing to the minus 1 initially, right? And the jth index will be starting from the array. It is going to traverse this. Okay, first of all, we are going to check this pivot element with the first element, right? So this first element is less than this pivot element. So we are going to just move the j, I and j for the forward position. First of all, we are going to increment the ith value by 1, and later we are going to exchange this I and j, these both values, and then we are going to increment this j value. This is the approach we are going to follow while doing this partition, right? And we are going to continue this approach, and like this afterwards we are going to check the pivot element with the array of this jth index, and 3 is smaller than 5. So we are going to again increment the I value. So I value will be pointing to this value, and later we are going to exchange this I and I comma j index value, these values, and then we are going to increment this j value. So actually some of you may have a doubt, right? Some of you might take the lower bound and upper bound. You're going to traverse like this way, but in this I'm going to traverse both I both this indexing from in the same direction. Okay, don't be confused about this. Both the way it will be same. Okay, so
Yes,
later
sir.
we are going to
Yes.
increment this I value after after checking this 2 and 5, where 2 is smaller than 5, right? So we are going to increment this I, and later we are going to exchange this I and j values until we find a element which is greater than pivot. We are going to increment this I value and j value, and we are going to keep on exchanging this I comma j values. When we came across the value which is greater than this pivot element, we are going to we are going to exchange this pivot element with that element, right? Finally, after we are going to exit from the inner loop, right? So let me compare this. Later the j value will be incremented from this, and now we are going to check 4 with 5, and 4 is smaller than 5. So we are going to increment the I value here, and later we are going to exchange this I and j values. After exchanging them, as these both are pointing to the same values, after exchanging here we are going to get the 1, and then in this position, and in this we are going to get 3, here 2. After exchanging I comma j, as they are both pointing to the same, every time they are pointing to the same index, right? That's why I'm taking the same elements in the new array. Okay, and here they are, after exchanging we will be getting 4. Later we are going to increment the value of j, and after incrementing the value of j we are going to check this 8 with 5. 8 is greater than 5, right? So now we just increment this j, and I will be pointing only at this point, right? And j is now pointing to the pivot element. Now we are going to exchange this pivot element with the I plus 1th index, right? Afterwards, so after exchanging this we will be getting 5 comma 8, right? I plus 1th index is this, which is pointing to the 8th element, 8th index, right? Later we are going to exchange this, and this is a new array we are going to get after completion of one iteration. So now our pivot element is here, as we have taken the pivot as 5, right? So what is the index? 0, 1, 2, 3, 4. So it will return the pivot index as 4. Hope you all getting this. And our aim is to find the
Yes.
third largest, right?
Yeah.
So k is equals to 3. So k, the pivot index is 4, but we need to find the k equals to 3. After the what is the size of this array? The size of the array is 6, right?
Yes, sir.
So the element we will be checking this pivot index. We have three conditions, right? If k equals to the pivot index, we will be returning this as it is the largest element. Okay, the kth largest element. And the other conditions are
No, if k
one
is
for
not if k is equal to pivot, if k is equal to
k.
length minus pivot.
Yes,
Like in this case, if we want second highest, then we will return pivot, right?
yes,
This
yes,
minus. If k is equal to 4, we cannot return the pivot.
yes.
Sir, you're not audible.
Right. Yes, I'm not. Okay, then. Now I'm audible.
Yes,
I'm audible. Okay, then.
yes, sir.
Okay, then. Here, what is the value of k equals to 3, right? So the third largest to find the third largest element, there is no. There are only two elements on the right side now after the pivot, right? After partition, we will be getting these two parts, right? 1, 3, 2, 4, and 5, 8. As we got the pivot index as 4. Hope you all getting this.
Yes, sir. Yes.
So we
Or
need the
better, we
third
can
large
say to the left we have 4, to the right we have 1.
to the left.
I mean,
Yes,
to the left of the pivot we have 4 elements, and to the right of the pivot we
yes,
have
yes,
1 element.
yes. To the left, we have four elements and we have only one element. So what is the chance that the third largest will be presenting? It will be presenting on the left side only, right?
Yes.
So as we all know this, at the pivot index, the elements after this pivot index will be greater than this this element, and the elements
Yeah.
on the left side will be smaller than this, right? Hope you all know the quicksort logic, right? After one traversal, the element will be going to its sorted position, right? So here, after this, the more we have the third largest will be presenting on the left side of this given array. So we are going to now take this new array, which is 1, 3, 2, 4, and in this we are going to again take this pivot element, which is 4, and later we are going to do the same traversal approach. Okay. After doing this, the 4 will be at this position only. It will return the index 3, right, as the pivot index, because there will be no change. These three elements are smaller than this 4. Hope you are getting this.
Yes, sir. But this looks like a
So here
complicated
these
method to find the key
yes,
element,
okay.
right?
Yes, yes. So here the pivot index, later it will be returning as this 3, right? Index 3, 0, 1, 2, and 3. This is the pivot index which is returned by after completion of this partition. Okay.
Yes.
Yes, sir.
So now we are going to check, and here this quicksort is a in place approach. Okay, the elements will be remaining in the same position, and the algorithm will be computing. Okay, we are not going to take any new array, or like in merge sort we are going to take a new list or new array, and we are going to shift the elements, right? So now
Yes.
in case of this quicksort, we are going to do this in the same position. So it is 3, 4, 5. At 4 we have 5 and 8, right? Now we are going to check, and it is a third element from the last, right?
Yes, sir.
So
X is 3.
so we can say that this is the third largest element from this, right? And it is equals to the Hope you are getting this.
Yes, sir.
So, actually, let us build this logic so that all your doubts will be cleared. Okay. Let us try to build this so that you have no doubts regarding this question. Okay, let us move. What is the function we need to build? We need to build this get largest.
So is this code actually, this logic is taking only order of n?
Okay, let me explain you the logic, the time complexity of after this code. Okay.
Okay, sir.
Mean it will be taking time complexity order of
Sir,
n
I
in
have
average
the
case.
code already written.
Yes.
I've already written the code. If we can save time, I can give my code so that you can explain or you can suggest better things.
Okay. Can you paste your code in the chat?
Yeah, just a second.
Is this entire code?
No, it's not allowing me to paste the entire thing, so I'm just giving
So
function by function.
here you are sorting, right?
No, I'm not sorting. I have taken the fast select, that median of medians approach.
Yes.
The first function, the mom function, is to get the proper median. I mean, instead of choosing some pivot.
Okay.
The second function is to partition, just like the way we do in the quick sort.
Yes.
Yeah, and the third function is to analyze the things on number of things on, I mean, number of elements on right and number of elements on the left.
Okay. Is this your code? Right? Is it right? Is the code is completed? Okay, only after kth logic.
Yeah, it's complete. I think there is a pasted. Can you go? No, no. These are the inner functions of the.
Okay.
Yeah.
What I'm missing? Okay, I need to paste
The
them in
best
the reverse order.
return statement. This partition, this def partition is an inner function. No, no, no. Keep it this way.
Okay, okay, this is an
Keep
inner
it, keep it
function.
like this.
Okay.
You just move, you just need to move the first. Okay, yeah. And the fast select is also an inner function.
Okay. That's it.
Yeah, and in the last line, the return fast select, that is this last line.
This should be order one, right?
Yeah, yeah, right, right. That's
Okay.
it.
Let us try to run this. It's executing these two test cases. Only 3 out of 5 test cases are passed, right?
Yeah, yeah, that's the problem.
For this question, are your systems also showing this system compatibility like this only?
Even when the test cases are big, we need to
I mean
scroll
about this,
right to see
about the screen. It is showing me variable length, right?
Yes, sir. It's
You
like
are
that.
in full screen mode, right?
Previously, my screen is like this, right?
Yeah,
It's
yeah,
not.
yeah, yeah. It's like this
It's
only
like
for
that
us.
only. Like that only.
For you, okay,
Yes,
I think
yes.
only for my screen it is showing like that.
No, no. It's the same for everyone.
Okay, then let us check this code. For the partition part, you have taken this index.
No, first
Okay.
I have taken the execution begins from the fast select function. First, I'll find a pivot based on the median of median approach.
Yes, this is the first function which is called, right?
Yes, yes.
Okay, first of all, you are calling this median of median by passing a list. Okay, then. And in this list, you are going to
Yes.
calculate.
It is the same as what professor has explained in the session.
Okay, and you are not getting it, right? Okay, let us,
Not the entire code is as professor explained. I have made few customizations to it.
let us check with the professor's code. So we get right. These are the wicked. As I have prepared different approach. I didn't know this professor approach. Okay, sorry for that. That's the question. Okay, this. Okay, this is not the. I think this is the. It is also the same one, right? This. Let us try to run this code and let us check what are the difference that you are facing in your code. Okay.
Yeah.
This is also similar to like this only. They have also implemented using this median of median approach. I have built this. Let us check this. Okay, then let us try to check this code. Okay. And here we have called the kth largest element, and in this function we are going to call this. Actually, these are also nested functions or what? Okay, here it is not nested, right? So you build your code in the nested form, nested by taking the nested function, right?
Yes.
Okay, here is your code. Okay, what about the base condition you have taken? Okay. So this code is little bit, I think these codes are little bit complex, right? So let me explain this code in a simple format, okay? By this quick selection approach, okay? You have taken this median of medians and
Yeah.
it is a bit complex type, okay? Let me explain you in a simple approach. Later we can discuss about this, okay?
Sure, sure.
So first of all, by taking this quick selection approach, which is in the same manner of quick sort approach, okay? We need to find the kth largest. Parameters passed for this are. Okay. Later, or we need to in the while finding this, we need to check the base condition, okay? Whether this k is greater than this array of this array or k less than 1. So do you understand this condition, why we are going to take this condition? First of all, we are going to check whether the index k is greater, the kth element is greater than beyond this array, or it is less than this array size, okay? If the array is of size 10 and if the kth position is 11 or 12 or it is greater than 10, and there is no point that we are going to get the kth largest element, right? Hope you are
Yes.
getting this. So if the even though if the elements are less than this one also, we can't find the kth largest element. So first of all, the base condition, we are going to check this. So if this is a scenario, then we are going to return nothing, right? We are going to return this none. Else we are going to do the quick selection approach. Okay. So we are going to call this quick selection approach. For this, we are going to pass the parameters as one is an array and the starting index, which will be 0 initially, and the ending index. The ending index will be length of this array minus 1. And we are going to pass the kth element. Okay, so here we are going to pass the kth element, sir. Length of the array minus k. As here we are going to check we are going to implement this partition approach as we are going to we are going to sort this in ascending order. Okay, so that's why we are going to check this length of this array minus kth index. Okay.
Okay.
Later we are going to implement this quick selection. The parameters of the array. Let me name them as low as the first index and high as the last index. And for the kth element, we are going to take k as an index. So now we are going to implement this. First of all, we are going to check the base condition whether low is greater than less than or equals to this high. Okay, similar to this quicksort approach, right? And later we are going to find the pivot element by calling this partition function. So this partition function will return as a pivot element, so that it will be simple for us to find the kth largest element. So for this we are going to pass this array first index and the last index. Okay. And afterwards, okay, after finding this pivot element, we are going to check whether this pivot element is equals to k. Okay, if it is equals to k, then we are going to return this. Here the pivot indicates the index. Okay, and if this index equals to the k, then we are going to return this element. And the other condition is greater than, if this pivot is greater than this k, and we are going to check towards the left side, left half.
Quick selection of array comma low comma pivot position.
Yes, array comma low comma pivot minus 1, right? And we are going to pass this k. So the other condition is we are going to check towards the right half. For right half, we are going to again pass. We are going to again call this function.
Pivot plus 1.
Now the first
Pivot plus 1.
And high.
Comma high comma k.
Right. Okay.
Yeah.
So when the pivot is equals to this kth element, we are going to return this element. This pivot is an index. Okay, it's not an element. And if the pivot is greater than this k, we are going to go towards this left half of the pivot. And if it and the other case is we are going to check towards the right half of the pivot, whether there is a kth largest element present in that half or not. So now let us build this partition.
There is a space introduced at the first line, I think.
Yes. Yes.
Yeah.
And first of all, we should take a pivot index, right? So let us take pivot element. Let us take the last element as a pivot element. After taking this last element as pivot element, first of all, let us initialize the I value to low -1. Initially, while I am explaining with an example, I have taken I equals to -1, right? J equals to 0, which is I minus 1 means I have taken I equals to -1. So now here we should take low -1. Okay. Then we are going to iterate using a range of low to high. We are going to iterate that half, and later we are going to. So as you all know, this partition function, right? Similar to this sorting quick selection, sort approach. This, this array of j is less than this pivot, and we are going to exchange them.
I equal to I plus 1 and
First of all, we should increment this I value by 1, and later we should exchange these values. We should swap them. You swap them with jth element. Okay.
J and I.
Array of y. Okay. Otherwise, we are simply incrementing this by 1, and later we are going to exchange this with the pivot one, right?
Yes. Not high, it is. It's not a pivot, right? No, pivot is an element.
Yeah. Okay. Sorry for the. It is high, right? The last element we have taken
Yes.
as a instead of high. We can also take instead of this place. We can also take this pivot, but for changing the
Lower.
values, we are taking in the form of indexing. Okay. Okay. Later we are going to return this I value because this I will be pointing to the pivot elements index. Okay. Okay. I think this is the code part. So let us try to run this. Okay, we have an error. Kth largest. The function is calling with the small k, right? Okay, you can see this. This public cases are all passed. Okay, this 5 out of 5 this private case is also all passed. Before explaining the time complexity part, are there any doubts from this regarding this code implementation part?
No, sir, it's clear.
Clear? Here we are calling this kth largest element. After call in this,
Yeah,
in
one
the
thing
first
was
step,
that in that first
yes,
function, quick selection, we wrote length of array minus k, right?
here this part,
Yes,
as
sir.
yes, we are going to implement this partition function to find to sort the elements in the ascending order format, right? So
Yes.
for in an ascending order elements, how will at which position the kth largest will be present? It will be present at the length of the array minus kth position, right?
Yeah, index will be k minus 1.
Yeah. Uh, If it is in descending order, index will be at k minus one, right?
Okay, in descending order it is, right?
Okay, and you can also build this code using this by taking the random element as a pivot. Okay, you should
Yes, sir.
just import this random library, and later instead of pivot index, you can take the random from the low to high. Let me take that. Let us try to import this.
Yeah, I was about to ask that, like, how do we knock off the worst case? So this is the way to knock it off,
Yes,
right?
yes. Just import this instead of this
And
line.
instead of array
You
of
can
high, we should,
yes.
yeah,
Instead of array of 5, let us take the pivot
array of random of
index. Should
random dot randint of.
from from low comma high, we have to select the random index. Okay,
Got
from
it.
this range only we have to select the index part.
And pivot is equal to array of pivot index.
Yes. Okay. Okay then. Let us try to check this part. Actually, we should also change this part also, right?
Is a pivot index. And J range should include high plus one, isn't it? Or
Yes.
for J in range of low comma high, earlier we excluded high because high has the pivot.
Yes.
Do we need to put high plus one there in the ending of the range?
No need for that. Let us try to run this. Okay. This. Only one test case is passed, right? About the second test case, the actual output is 7805. For the first one, it is showing us a wrong output, right? Let's check this code once. So coming to this, we have imported this
Can
random.
you try with high plus one? I suspect
Okay.
for
High plus
J in
one.
range of low comma. No, not there. Not there.
Yes,
J in
yes.
range
Sorry
of
for that.
low comma high plus one. Randint obviously takes both the bounds.
Yes. This. Okay, I think I have missed this over here. I think so. I get this now. It is not. We can iterate only up to this I, but after finding this pivot element, here we have find this. We have taken the random element as a pivot, right? So by taking a random element, we don't know which element has taken as a random one, right? So afterwards, we can't traverse whether completely of the array, right? So we should replace this pivot element with the first or the last index part, last with the last element, so that we can able to do this partition part. Okay, to do this partition, first we need to shift this pivot element to the first index or the last index. Hope you are getting this. So instead, if we don't shift this pivot index to any of this position, if we do this, it will it doesn't give us a correct solution. So let us change. First of all, let us exchange this way of pivot index, comma high.
Okay, then this might be the problem in my code as well, because in my code also, if I take some median of median,
Yes.
somewhere in the middle, one value will be coming as pivot, right?
Yes, yes. That's why we can't able to traverse this entire part, right?
Okay, okay. So we should put it at one of the edges, keep it undisturbed, and we should
Yes.
arrange the other
Yes.
array.
Later, after completion of the
Okay, I get
traversal,
it.
finally we are going to exchange the values.
Okay, I
Okay
get
then.
it.
And here this high remains same because the finally the pivot element is pointed to the last index. Okay. Are there any other changes? So low -1. Okay then. Now let us try to check this code. Okay, now you can see the two public cases are all passed. Let us go for the where are they? Let us submit this and let us check the whether there is okay. We can see this. The 5 out of 5 private cases are also passed. Okay, are there any doubts regarding this implementation part? Or we can go to the time complexity. What is the time complexity it is taking now? Okay, then let me show.
Can you scroll up to the part where you have did
Yes.
that exchange?
Yes. That's here instead of taking this high, we are just taking the random value as a pivot one, and we are exchanging the high value with the pivot element. This is the only step,
Okay.
so that we can make the time complexity to an average case. Okay, instead of to avoid this worst
Okay,
case of
okay.
order of n square, we are doing this part.
So it will be n log n if you choose the pivot randomly.
Yes.
So it will be n log n on an average.
No.
So basically,
Doesn't
what
take.
we studied was if the pivot is not picked properly, it could create worst case scenario where it could be order n square. But if we choose randomly, then on an average it will get n log n.
No. It will take only order of n time, right? The k into n time. Okay.
What is
Oh yeah,
saying
k
is
log
for
n.
quick sort. That
In
is
quicksort.
completely quick sort. This is quick
Okay. In
select.
quicksort. Yes. In quicksort, we are going to travel in both sides, right? And in this quick selection, only we are going to go towards the part where the kth largest element will be present. Only on the one side, one half we are going to traverse. Okay. On one half only we are going to do the solution part. We are not going to do the solution on both the parts. Okay. Both halves, both the left and the right halves.
Got it, sir.
See here, as we have taken a condition here, right? we are mentioning the if else conditions. Coming to the quicksort, we are calling these functions, right? We just call these functions instead of going to one side. We go for two sets of the pivot element, both the right side and the left side. So here we are going only one side of the one part.
Got it.
Okay. So by this quick selection approach, we can reduce the time complexity to order of n. On the worst case, it will take us order of n square. By taking this random value as a pivot, we can reduce the worst case scenario also. Okay. Hope this is clear. The first question. Are there any doubts regarding this first? Yes. Yes. What? Are there any doubts regarding this first question?
Yes, sir.
Okay then. Shall we move to the next code? Okay then. Okay, this is clear now. Let me read out the question for you. Given a Python function, Karatsuba of x comma y that implements a Karatsuba's algorithm that multiplies two integers x and y recursively. Length of integers x and y may or may not be same. Refers to the definition of the function Karatsuba x comma y, and complete the Python function calculate and assign, and we need to complete this function only that accept the integers x and y and return the five variables that will be used in the subsequent recursive calls of this Karatsuba function. Okay, so we need to build this function and it should return the these five values. Okay, and here we can see the hope you do you know what is this Karatsuba algorithm means?
No, sir.
Okay, and do you know this multiplication of two numbers? How we multiply two numbers?
Is that also an algorithm form?
Yes, let me. Okay, in our school, from our school, we know multiplying two numbers. For multiplying two one digit numbers, it is simple, right? We can directly know the answers for that. We can directly say single digit multiplication solutions. But for the multiple digits like 15 into 13, how we will be doing? We will be multiplying this
Positions and doing that, we know.
3 and later 1 into 3.
Yeah, that is
and, yes.
So you want to
Like
do
this
it like
we are going to do. Later we are going to add these parts, right?
Yes, sir.
Got it.
So like this we are going to do this approach. And in this, how many elements we have here? Two elements in this first integer and two elements in this second integer, right? So we are doing this multiplication part 4 times, which is 2 into 2 times. So if in case if the integers are of size, if there are a large integer, like if it is a large integer, let me say like so and so. So these type of large integers will be used in like in cryptography or in any kind of Bitcoin algorithms. These large integers will be used, right? So to compute this multiplication on these large integers, so it might take n cross n, which is n square multiplications, right? So it is a very large time complexity. So we are wasting a lot of time at this part only. So to reduce this time complexity, we have we have this Karatsuba algorithm. Okay, and by this approach, we can reduce the time complexity to order of n power 1.585, which means roughly it is order of n 1.5n. Okay, we can reduce this order of n squared to order of 1.5n. So this is a better approach, right? Instead of doing this multiplication these many times, we can reduce the number of multiplications and we can optimize the multiplication operations. Hope you are understanding this.
Yes, sir.
So here, let me explain you clearly with an example. Let us take an example of, we have 20 and here we have 30. Now, what we normally by elementary approach, what we will be doing, firstly we will be multiplying this with these two
3 into
elements.
7. 3 into 2.
So we will be getting here 0 and here 6,
6.
and later we are going to do this.
1 into 0. 1 into 2.
So we will be getting this 260, right? So here we are going to do n minus 1 additions or n additions. Okay, these many additions are performed, plus and n square multiplications are performed, right? Here in this example we have done 4 multiplications.
Yes.
And if there are carries, okay, if we have here 9, 3 9s are 27, right? We will be having carries also, right?
Yes.
So if in the worst case, if every element has a carry, and we need to again increase the number of additions also. So the number of additions might also increase up to n square or n, okay, or 2n times. This so these much of time is wasted by doing this multiplication in our in the approach of our elementary approach, okay, elementary school approach. So instead of wasting this time over here, we have an algorithm called Karatsuba algorithm, which will reduce the time complexity to order of n power 1585. Okay, n power 1.585. So we can reduce this to order of n square to 1.585. How means Karatsuba has founded that. Let us take an integer. Let me take an integer. Okay, 1385 and 111. So if I need to perform a multiplication on these two numbers, he has divided the numbers into two parts. Okay, and this is the first integer and this is the second integer. If we divide this into two parts, let me assume this part as A, this part as B, and this part as C, and this part as C. Okay, from this he has found a logic that we can reduce one multiplication. Okay, we can do this in three recursive multiplications, and three recursive additions. So instead of doing this 4 times, we can do this multiplications in 3 times only. Let me explain you how it goes. Okay, okay. So if x is an integer and y is an integer, let me take an example and explain you. It will be very clear for you. So if x equals to this, let me take the large integer, so it will be helpful. If x equals to this part, and if we divide this given integer into two parts, 146 will be one part and 123 will be one part. How we can divide this into two parts? We can divide this as 146 into how many thousands it is, 3 plus 123. What is the value we will be getting after doing this part? We will be getting this same value, right? Hope you're
Yeah.
getting this.
It's a position value basically. 146 as
Okay.
But
Yes.
how do we,
Okay, listen.
know at the first time that it is 10?
First of all, we need to divide this into two parts, right? So listen this carefully until the end, so that you will be able to understand
Okay,
this.
okay.
So here we are dividing it, right? So later, what is the value we will get in? 146 into 10 to the power of 3 is a one value, plus 123 is another value. So we can take this as A, and we can take this part as B. And let us take another integer y as 350. Okay, and this is another integer. And how can we take this part? We can take this as 352 into 10 to the power of 3, right? Which means 352,000 plus 120. So this 1000 part we can write this as 10 to the power of 3. Okay, plus 120. So in this we can name the variables. We can take this as C and we can take this as D. So like this, we can divide this into four parts. Okay. For every integer, we should divide this, and we should solve this, and later we should conquer the solution. As this VKT is on divide and conquer approaches, right? This is one of the application problem related to this concept. So let me take here. We have taken this A, B, C, D. These are the values which we have taken. So our aim is to find x into y, right? As you can see, I have taken this x and y, these values 146, 123, and this is 352,120, and this is a y value. So now we are going to perform this multiplication of these two numbers. Okay, so these two values are very large values, right? So for the values which are one digit, we can directly compute. Okay, so for this large integers, let me explain you this solution for that. If you perform this x into y, keep this this is the decimals, 10 to the power of n plus b c into 10 to the power of n by 2 plus d. Okay, what is the value of, okay, this is the notation for this. Okay, I have written this in the form of a notation. This is the a value, right? A value part. For generic condition, I have taken this for so that you can apply this for every problem. Okay, here n value represents the number of digits. Okay, and in the given x and y integers, we have 6 integers, right? In this, we can see 1, 2, 3, 4, 5, 6. So n value will be 6. So we are going to find the number of n value. So here I am applying this same this a comma b values in the form of a formula, so that we can implement this. Okay, do you understand this part? How we have taken this? This is x and this is y. We have taken x into y, right? X and y, x into y format. This is a 10 to the power of n by 2. Okay,
Yes, sir.
so here in this integer we have, in these integers we have 6 digits. So 6 by 2 means 3. Let me implement this. What is the value of a is 146. 146 into 10 to the power of 6 by 2, where n value is 6 from this question. So we will be getting here 3 plus b. What is the value of b? 123 is the value of b from this. And into the value of c is from here, okay, 352. 352 into 10 to the power of n value is 6. So 6 by 2 is 3 plus d is 120. So this is the same expression we have got here, right? So this expression we have done represented this in the form of a formula. Okay, like this. So let us simplify this. Okay, let us try to simplify this. So instead of taking these numbers and simplifying, I have taken this in the form of a variable, and later we can simplify this easily. Is it 10 to the power of n by 2 plus b, and c into 10 to the power of n by 2 plus d. So let us simplify this. Okay, we can, this is like a plus b into c plus d, right? So we multiply this a into c and b into d, ac plus ad plus bc plus bd. Like this we simplify, right? Hope you all know this, right? How to
Yeah,
simplify this given
yeah.
in the form of a parent. Yeah.
The distributive
Okay.
property.
Let us simplify it like, yes. Let us simplify this. So what we will be getting, a into 10 to the power of n by 2, and this into c into 10 to the power of n by 2. This is the first part, right? Plus later a with this d, ad into 10 to the power of n by 2, plus next this b into c, plus, okay, b into c into 10 to the power of n by 2, and b into d. Okay. Later, let us simplify this more. You can write this as AC into 10 to the power of n by 2 into 10 to the power of n by 2. We can write it as this is as 10 to the power of n, right? Because n by 2 plus n by 2 is n, right?
Yeah.
And
Yes.
later, this part AD into 10 to the power of n by 2. And from this AD into 10 to the power of n by 2 and BC into 10 to the power of n by 2, we can take 10 to the power of n by 2 as common, right?
AD plus BC.
Yes. We can write this as AD plus BC into 10 to the power of n by 2 plus the remaining is BD. So now we can see how many multiplications are there in this simplification. We can see here is one multiplication, here is one, and here is one. And how many multiplications we are performing here? 4, right? But we don't need this 4 multiplications. We can reduce this multiplication because this AD plus BC, we can get this from these values, okay? Minus AC minus BD. So we can reduce this multiplication to 3. You can see this is BD. Now we can see here. If we simplify this, what are the values we will be getting? AC plus AD plus BC plus BD minus AC minus BD. So these are the values which we will be getting after simplifying this part. Okay, and we can cancel this AC and BD. So what are the values remaining? AD plus BC. So this is a value which we should be computing here, right? So to compute this directly, we need to perform 2 multiplications. This A into D and this B into D. So we can avoid these 2 multiplications and we can use this. You can do this only 1 multiplication here. Hope you are getting this. As this AC and BD are already computed here.
Yeah. So leveraging the existing calculations, so it will be faster.
Yes. So here we have already computing. We will be once computing this AC and this BD will be already computing. So to reduce this number of multiplications here, we can simplify this in the form of like this, right? So that there will be only one multiplication we are doing here. And other part we are going to do this addition part, right? By simplifying this one, we will be getting this AD plus BC only. So this part is clear for everyone?
Yes, sir.
So how
Yes,
is
sir.
so our task is to find this multiplication. So if this is a single digit, we no need to find this. If A or C, either of them is a single digits, we can directly multiply them. So if this is a multiple digit, okay, if this is 15 and if A is 15 and C is 16, so we again do the recursive approach. Okay, we again call the function for that. So let me again show you. I have taken few pictures over here. Visually you can it will be very clear for you. Okay, where are they? Okay, here are the pictures which I have taken. Okay, so by doing the elementary approach, this is a way we are going to do this multiplication part, right? So these many multiplications are done while we are doing this in this approach. So these many additions are done. 4n square additions are done in the elementary approach. So this n square, these are all carries part. Okay, in the worst case, it might lead up to n square because n square multiply on n square multiplications. If every element has a carry, there will be n square carries, right? Hope you are getting this part.
Yeah. So
This
all
is
the
an
numbers are, let's say, 999, right? So you'll have carry.
Yes, this is an elementary school approach. In our schools, we used to do in these approaches. But by using this Karatsuba algorithm, let me share you this. So if our aim is to find this multiplication of these two numbers, okay, 146,123 and 352,120. So if we want to do the multiplication of these two numbers. So here we have 6 digits and here we have 6 digits. So multiplication of these two, it will take us how many times? 6 squared, right? It will take us 36. 36 multiplications are needed to do this part, to get the solution part. And for 36 multiplications, we also need the 36 additions also, right? Along with this 36 multiplications. So after performing these multiplications, we also need to add every column, right? So we also need it might not be 36 roughly. I'm taking this 36, okay? So instead of to avoid this part, we have this Karatsuba algorithm where, as I have told you, this you can see this, right? This is an example. It our aim is to find AC value and BD value and AD plus BC value, right? So these are the three multiplications only we need to find instead of doing this every multiplication part. Hope you are getting this. Here we need to do 36 multiplications for this problem here. But by using this approach, we need to do this multiplication on this part, and this part. Only three recursive multiplications only we need to do. Why we call this as recursive multiplications means if A and C are also a multiple values, okay, if it is also a large number, we can again call this function recursively, so that it will be going until the number A comma C values are a single digit numbers. So on single digit numbers, we can directly say what is the value, right? We can directly give a solution for a single digit numbers. Hope you are getting this.
Yeah, that's the base case.
Yes, and here let us see here. We have called this multiplication for these two numbers. For first of all, we need to find this AC value, right? We need to find AC and this BD. After finding AC, BD only, we need to find this AD plus BC. Hope you understand why we need to find this AD plus BC after finding these two values. Because we are going to use, for AD plus BC, we are going to use this approach, okay? C plus D minus AC minus BD. As we are using these values over here to reduce the number of multiplications, if we do directly on this, it might take us 4 multiplications. By doing like this, only one, we can reduce one multiplication part. Hope you are getting this.
Yes, sir.
So
Yes,
that
sir.
we can only do this one multiplication over here. So these AC and BD values are computed before this before this step only, right? So first we are going to find this AC part, and we can see 146 here. If we divide this, 146 is the A value, this is a B value. Every given integer, we are going to divide this into two parts, okay? This is a C value and this is a D value. Now we are going to, this 146 is a multiple value, right? It is not a single digit. So we are again going to call this recursive function, okay? On 146 A and C, right? What is the value of A? 146. What is the value of C? 352. So we are this AC means A into C, okay? So we need to multiply this A and C. We can directly multiply, but to avoid this unnecessary multiplications, okay, to avoid this unnecessary multiplications, we are again going to apply this algorithm approach. So 146 and 352 are called over here. Later we are going to divide this 146 into two parts, okay? This is 14 and this 352 is a multiple value, so we are again going to divide this part. So this is a, this is a new B, this is a C, this is a D, okay? So now we are again going to call for AC value, okay? To compute this AC value, now here also we should compute this BD value and this AD plus BC value, okay? And now to compute this A into C, we are again going to call this function, and later on 14, A is 14 and here C is 35. So we are going to call this function, and this is also a multiple value. So after we divide this into two parts, so A value, now here A equals to 1, B equals to 4, C equals to 3, and D is 5, right? From these values. Hope you are getting this.
Yeah.
Okay, then now these are all single digit values, right? So in this we are going to compute this a into c. So a into c, what is the value of a? A is 1. Multiplication of a into c, c is a 3. 1 into 3, what is the value we are going to get? We are going to get this 3, right? Answer. So this is a answer for AC. And we also need to compare this BD value. So for BD, what is the value of B? B is 4. So D value is 5. So 4 into 5, what is the value we are going to get? 20. 4 into 5, it is 20, right? So this is the value of BD. So later, what is the remaining value we need to compute? Can anyone answer?
So on the right hand side, so we have 46 means we have to call k of, okay, so 6 actually we don't need, right? 6 is,
Yes, actually, we need to compute this separately. Okay, this BD
yeah,
side. Actually, here we need only A into C, right?
right, right,
So we are going to take this A into C, A and C values only towards this side. Okay,
yeah,
this here A is 14 here.
yeah.
So B is 35. These are also two-digit values, right? So instead of wasting this number of multiplications, we are going to reduce this number of multiplication by calling this function recursively. Okay.
Okay. So that means on the right hand side, K62 should be there below right hand side of that K146 352 to make it complete. Right hand tree, recursive tree with the drawing. So K6 by 2 on the right, and then similarly on the right hand side also will expand. Uh, Makes sense?
Okay. Sorry for that. Am I audible now?
Yes. Sir.
I got
Yeah,
disconnected
no
for
problem.
like.
You have to share the screen again.
Okay. Actually, I was teaching like that only. I didn't aware of that.
So yeah, I mean, I think we lost audio about 30 seconds ago or whatever. Yeah,
30 seconds ago. Okay, sorry for that.
no problem.
Okay, is my screen visible now?
And now, yes.
Okay, now here we have computed this AC value. Okay, and for this function we need to again compute it, right? For k of 14 comma 35, we need to again compute this AC value, BD value, and this AD plus BC value, right? So we need to again compute these values so that we will be getting the solution for this part, right?
So will such problems come from OPP?
What
Yes.
is
This
that?
is
Actually, this logic is actually this logic is difficult, but this solution is very simple. Okay. For
okay.
actually, I'm explaining for every okay,
So basically, sir,
for
what
every case
happens
I am
is,
explaining here.
yeah. So what will happen is, if you look at the sequence of the calls, in the top level we start with 146, 123, 352, 120. So on the right hand
Yes.
side, 146, 352. On the right hand side, it will be 123 and 120, right? So all are like second level is all three-digit numbers. Then each of them will be like a binary or tree, whatever it is, right? So then K146 will have two children, right? 1430 K1435, then K62. K62 we stop because these are all single digits, and 1435 will also
Yes.
have 1 3 and 4 5, right? So that will stop like what you have actually.
Yes.
So what you've
Actually,
done here,
here
yeah. Why you have 5 8?
here
I
we
don't know.
after are you not able to not able to understand this clearly?
No, that
Let
five
me take a
eight that 5 8 part is not clear. Like the third one,
This one
the 5, 8, 40. Why that call is happening below 14 and 35? 1,
below
3, 4, 5
14 and
makes sense. Yeah, so maybe that's that AD plus BC some.
this is clear for you.
Yeah, that one is very clear.
For this part only, you're not able to understand this, right?
Only the third part, 5, 8. See,
This
1, 3, and 4, 5, that anyway will come from the root. So basically, we have to go all the way to single digits. Then that 5 and 8, it is probably AD plus BC
yes, only
something.
only about this part you are confusing, right?
Yeah, yeah, yeah.
Actually, this part, for every function, for every k, we are going to call this on AC, and we are going to compute this BD, and later we should compute this AD plus BC, right?
Right.
This third function. So for computing this third function, instead of doing this multiplication two times, we can avoid these two multiplications by by this simplification, right?
A plus B
A
to
plus
C
B
plus D.
into
Yeah.
C plus
And
D
deduct
minus
both the
AC
products.
minus BD,
That's,
right?
yeah.
So that we can reduce this number of multiplications. So here
Right.
A plus B, we can see what is the A plus B, 1 plus 14. Here A is 1, B is, you can see from here, right? 14, A, B. As we are dividing this into two parts. Here in 35, we are going to divide this 35 into two parts, right? This is C and this is D. And what we are doing, A plus B and C plus D. A plus B means 5, right? So we are going to call this K of 5. And C plus D, what is the value of C plus D? 3 plus 5 is 8. So we are going to do this Karatsuba algorithm on this values, okay? And 500. These two are single digit values, so we can directly multiply these values and we can get this 40. Now this is clear for you?
Oh, okay. Yeah, yeah. Now I got it. To get that third number, you are doing A plus B is 5. Okay, yeah. 1 plus 4. Okay, then 3
Plus
plus
you should do this A plus, you should do this A plus B and C plus D,
1. Got
okay?
it.
Or instead of calling, let me show you how the functions will be called, okay? Let me clear this part.
Got it. Got it. Got
Let
it.
me
So,
clear this.
so that means if we
Okay.
solve the recurrence equation, it will be something like a log base to 3. So then,
Yes,
yeah, that's where
yes,
that
yes. It will
1.5
be
is coming
for
from.
it is like similarly like binary tree. Okay, for binary tree we have only two ways, right? For
Correct.
this we'll be having three recurrence equations.
So it will
Okay,
be log
for
3 with
finding
the
this
base
AC,
2.
yes, yes, it will be like this. Okay,
Okay, okay. That probably is 1.5. I have to
so
check the table.
n power this n power log 3 is, we know this log 3 value is approximately 1.58 like this. Okay,
That
so
was
our
great.
time complexity will become 1.585.
Got it.
Okay,
Makes sense. Because we have
like this
three
we can
recursive
reduce
calls,
this
that's why.
time.
Because we have
Yes,
three
yes, for
recursive
three
calls.
recursive calls.
Yeah.
Okay, I will also explaining the recurrence equations also, okay, for this problem, okay, how we will getting this 1.58, okay. So now let me explain you how this function calls are made, right? This k on a comma c it is made for this part. No, for AC, for BD it is on b comma d, okay, like this b comma d. And the last one, for this it is called on a plus c comma a plus b comma c plus d, okay.
Got it.
As it to find this AD plus BC, we are going to call A plus B and C plus D. Okay.
Yeah. So that
So
means that
you might be
that
confused that
now, so that ADBC will be then 40 minus 3 minus 20,
yes, 40 minus,
20 minus
yes, yes.
3.
Later,
Yeah.
only for the function call, we are going to include this part. This is out of this function part, right?
Right, right.
Okay, sorry. Am I audible?
Yes, sir.
Okay, then. Hope you understand this logic. Why we are calling this here?
Yeah, yeah. This is not clear, sir. This is not clear. That
Only you should keep in mind that here we are going to take this a plus b part and here c plus d. Okay.
so
So
the
you might
only
be
thing I
confusing
see
how we
here is,
got.
so the only thing is that A plus B and C plus D sometimes, not always, if it
Yes.
becomes a two-digit, then it may carry and it may
Yes.
create another recursive call.
Yes. For every time while calling this function, we need to check, right? Okay. We
Correct.
need to check whether it is below 10 or okay. Below 10
Right.
or greater than 10. Greater
Right.
than this one.
I
So
think
if
it
it
makes
is
sense.
between this, we can directly compute these values. Okay then.
Got it.
So like this, we are going to compute this AB, this AC, this BD, and AD plus BC values. And later, after computing these values, okay, after computing these values, we had a formula, right?
I think that
Okay, here is a
yeah, yeah,
formula.
that 10 to the
Here
power
you
n,
can see.
yeah, yeah, 10 to the power n.
Yes, yes. This AC into 10 to the power of n by 2. What is this n by 2? This is 3, right? 6 by 2. As the number of digits here are 6. So 6 by 2 is 3. Okay. So 3, but okay, sorry. The first one,
So
we are going
every
to
level the
multiply
n is
this
changing, right? At the level
3 to
1, the n is 3, but in the level 2, on the left hand side, n is 2, but
yes.
right hand side, n is 1. So basically, at
We
that,
need for the given question only. If we change this, we have to take this n value only because this
right,
is in thousands, okay, and we are reducing these thousands into hundreds. So the answer might get in hundreds only, okay. So
right,
if our aim is to compute this 12 into 10, and if we are going to take this 1 comma 2 like this, okay, 1 comma 1 like this, so these are in units only, right? If we do computations on, if you do multiplications on this, we will be getting only answer 2. And from this, okay, let us examine. Okay, let me, for example sake, let me tell, if it returns 3, if this returns 5, so by these values we might not get the correct answer, right? If we take the n value as 1, because there is only single
oh yeah,
digit.
yeah, got it, sir. Yeah, yeah. So we have to go to the original
So
number.
yes, you should keep this in mind that the original value will not be lost because it is in thousands. Large values will be there. Okay. Okay. Here we should take this. Keep this formula in mind. Okay. Here you can see this. After computing this AC value, BD value, and AD plus BC value, you need to substitute them in this given value. Okay. After substituting, you will be getting the answer for this part. So here you can see. Okay, you can see AC into 10 to the power of 2 into half. Why 2 into half? Here we have, for A, we are having A into 10 to the power of n by 2. For C, we are having C into 10 to the power of n by 2. So by multiplying this A into C, what are the values we get? AC into 10 to the power of n, right? And because n by 2 into n by 2, 10 to the power of n by 2 into 10 to the n by 2, we will get 10 to the power of n, right?
Yes, sir.
Yeah, it is like a
Hope you
quadratic.
understand this.
Yeah, yeah. One term will
Yes.
be 10 to the power n. The two terms will be n by 2, and the other one is just that CD is a simple multiplication. There's no power.
Yes.
So one term
And
will be
here
10 to the
half.
power n. Yeah. The middle one, 80 plus BC, will
Here
be
half.
n by
Okay.
2. Yeah, makes sense.
Oh, yes. Here we just need to substitute them. Okay. From this we can see. Okay. Let us take this part. Okay. Let us substitute these values in this. This is the AC value. This is BD value. Now this is AD plus BC value. Okay. This is for this part we have computed only A plus B comma C plus D, the multiplication of these two values only. But later after computing this, we got 40 right here. 5 into 8, 40 we got here. But later we need to substitute them in these values. Okay. 40 minus, what is the value we got on AC, on doing this AC? We got 3, right?
Yeah,
We need to subtract this 3. And what is the answer for BD? This 20.
20. Yeah. So
So we need
17.
to subtract this 40 minus 3 minus 20. It will be 17, right? 40 minus 23, we got 17. So this is the value for AD plus BC. It is the original value. It is not the value, okay? It is the value of only the multiplication of a plus b into c plus d. Okay, this is not a value for ad plus bc. Keep this in mind. Okay, and later we need to substitute the values in the result. Okay, this is the result part. This is a result equation actually. AC into 10 to the power of n, and here 2 into half, where half is the n by 2 value only. Okay, I have taken it directly here, plus AD plus BC into 10 to the half, here n by 2 we need to take here. Hope you all know where the simplification has come. Okay, from the given multiplication only we have drawn a simplification of this, right? Okay. Okay, then let us substitute these values. Here AC is 3, 3 into 10 to the power of 2. Here, what is the value of half? We got here 1, right? Let us check this. How it is n equals to 2, okay? Okay, as you have, someone has asked me about, right? Here the length is only 2. We should take this length or this length. This is a doubt someone has asked previously, right?
Yeah.
So here it is, we can see this, they have taken the length of this only, this function only. For every function, the length will be taken independently. Okay. Sorry for that. Previously, I
Yeah,
have made a
because
mistake.
when the recursive call, the local variable will keep all the things in that stack
Yes,
call. Right?
yes.
Yeah. So then,
We need to keep, yes,
correct.
we need to pass a local variable for this n value also. So by passing this n value also, it will be computing with these values. Okay. So recursively after this solution will be returned to this value. So this solution will be a part of this AC for this function call. Okay. This entire solution we have done now is this AC of this function call. Okay. So we need to compute this BC value, BD value, and AD plus BC value also. This is only the solution part for AC of this function call. Hope you understand this.
Yeah.
Okay, let me show you the full tree. Okay, where it is. Okay, then. Here is the full tree. Okay, keep a look. Okay, can you see this tree part, the full tree part?
Yes,
Yeah,
sir.
so that third one is 146 plus 123 and 352 plus
Yes.
120. Yeah. Now I see at every level there is going to
Yes,
be three
yes, this
calls.
is divided into two parts, right?
Correct.
So this is a part of B. This is C. This is D.
Yeah.
So we are calling this BD here. This, and here we are calling this A plus B plus C plus D.
Yeah.
Okay. As I am mentioning that it is the AD plus BC, but we are calling for A plus B and C plus D. Don't get confused because it will be confusing at the only for the third function only. It will be confusing. Okay. Okay, this part is clear. Can you look at, keep a look
Yeah.
at this. Okay.
So second level is very clear
Okay.
because 3 by 3 and then ABCD and then A plus B, C plus D. But the next level also we are taking left side is 2, right side is 1. So that is also clear. I think it
So
makes sense.
to compute, so keep in mind that firstly we need to compute this A into C. So this A into C, if these two are not single digit values, we again need to call this function. Okay, keep this in. Okay, secondly we need to find this B into D, right? So this is also similarly 1 and 2 are same, both are same. For computing this third one, we need to pass A plus B as one parameter and C plus D as another parameter. This is one parameter, this is one parameter, and we need to add a multiplication of these two. Okay. Hope you are understanding this.
Yeah.
So after for this third one, we have some other extra calculations also, computations. Like after computing of this, we need to subtract this AC and BD part. After subtracting this only, we will be getting this third function's output. Okay. And after computing this AC, BD, and this AD plus BC, we need to substitute these values in the given simplified equations, as we got a simplified equation previously, right? And where the simplified equation looks like this: AC into 10 to the power of n plus AD plus BC into 10 to the power of n by 2 plus BD. So this is a simplified equation. So this is the result. Okay, we should return this. So every time here
Last term
this
was
result will be
CD, right?
yes.
Last term was CD, not BD.
Last was
That is CD, not BD. The last one without the
okay. Let us have a check. No, it is
BD,
BD.
BD,
only.
BD, BD, BD. Yeah, A plus B, yeah, BD, BD.
Yes. Okay.
Yeah, this one clear.
Okay then. For regarding this logic, it is clear for you. Are there any doubts regarding this logic? This is simply a recursive equations, right? And let me explain your time complexity, how the time complexity will be. Shall I take another example, or this example is enough for you?
It's clear, sir.
It's
It's
clear.
a recursive, right? So
then.
we have to just understand the main
Are
part.
there any doubts regarding this logic?
No, it's clear. We're making it into a single digit.
Yes, making it single, and we are going to reduce this number of multiplications for
Yes.
every
And
time.
only 3 recursive operations of AC and BD and AD plus BC, which will be eventually done as A plus B and C plus D. And
Yes.
yeah, that is clear, sir.
Yes, here you can see every time we are going to compute only 3 multiplications. We are avoiding the 4th multiplication. Here we have 4 multiplications, right? This one, this one, this one, this one, this one, right? 4 multiplications we have, but we are reducing this 2 multiplications into 1.
Yes, sir.
Okay, by reducing this multiplication, we are going to reduce this time complexity also. Here we have 3 recursive calls, right? How does the recurrence equation, okay? How does this recurrence equation will look like? 3 into 2 to the power of n by 2, right? We are going to reduce this by n by 2 size, right? These many recurrence equations are called, right?
Okay.
Yes,
It is clear.
some addition.
And
of
for
our
every yes, and for every equation we are going to compute them for order of n time. Okay. For let me explain you this, and now
Sir,
we got a recurrence equation, sir.
3 n by 3,
Yes.
right? We are making into 3 portions, right?
3 n by 2 portions only. Okay, this is n by 2 portion, n by 2 portion. Combination of these 3 n by 2 portions will become 3 n by 2, right? Okay. This is not n by 3, okay, only n by 2, okay. But 3, they
This
are
is very similar to the quiz one question we had, where in the merge set, every partition we are dividing into 3 parts. And
okay. It is like okay, yes. That type of questions will be asked also, right?
actually, that was in the quiz one just finished. Merge set, there is instead of splitting into 2, the question said you are splitting into 3 parts.
Yes. And coming to this, as you all know, this binary search, right? By using how do we search this binary search? We keep on computing the middle value, and we are going to search that, right? So in this binary search, it is only n by 2, right? T of n by 2. Why?
Yes, sir.
We are not considering the other part. We are only considering about the single part. So that's why only it is n by 2. If we consider the both this part, it will be 2t of n by 2, right?
Yes.
So if we consider the third part also, it will become 3t of n by 2, right? So here in this given problem, we have 3 recurrence equations. So for 3 recurrence equations, we got 3t of n by 2. So for every recurrence equation, it will take order of n time, okay? For computing this every recurrence equation. Okay. So plus n we take here. So if we keep on computing this, if we simplify this, Let us try to simplify this part also.
So that n is coming from n order 1 additions, right?
బయట జరిగితే పైసలు ఎక్కువ
Yes.
వస్తాయి మాకు. ఈ రూమ్ లో ఆ రూమ్ లోకి వేస్తారు, ఆ రూమ్ అక్కడికి
Okay then.
మారుతారు. అయితే అది కాదు ఆగేస్తుంటారు చేసేది.
N is coming. I think N is coming from this number of digits part, right? As previously, this is n square, right? This time complexity. How we got this n square? This n into n multiplications are done on n elements. Oh, okay. Like this, we got this n square part, right? This n represents the number of digits. Okay.
Yeah, so our number of additions will be the number of digits. 2 times
Okay.
that.
Number
So
of
it's-
multiplication. Okay.
Yeah. So it is
Okay.
basically
We are going. We are going to use them.
digits. Yeah.
Yes. So let us try to simplify this recurrence equation. Now, if we again for this t of n by 2, this is the recurrence equations for t of n. For t of n by 2, for t of n by 2, if we again compute this, what is the value we are going to get? We are going to get for t of n by 2, 3t of n by 4, right?
Yes, n by 4.
3t of n by 4 to order of n by 2, or let us remove this part, n by 2, right? So let us replace this over here so that we will be getting 3t of n by 4 plus n by 2 plus n, right? So if we simplify this part, we'll be getting 3 square t of n by 4 plus, from this, if we take this as common, we will be getting it as, if we take n as common, we will be get by, okay, from this, if we multiply this inside, it will be 3n by 2 plus n. From 3n by 2 plus n, if we take n as common, we will be getting this 3 by 2 plus 1, right? This part is clear for you?
Yes, sir.
Now we got to case steps.
Okay, so if we keep on taking like this, it will go up to
3 to the power
3
k.
for
And the kth
log n
step
times.
3 to the power k.
this k. This
Okay,
k
you're talking
equals
about
to
the
log n
parts
here.
of the
Okay.
base case you're saying. Okay, okay. Yeah, we have k equal to log n. Yeah,
Okay.
yeah, got it.
Okay.
Yeah.
Plus this. Okay, let me explain you one more step also. It might be clear for you. Okay.
Last one will be order 1. Basically, we need a single digit.
Okay. So if you again call this on t of n by 4, what is the value we get from this? We'll be getting this 3 into t to the power of
N by 8.
n by 2 to the, let us replace this as 2 square, so that we will be getting this 2 power cube, 2
Yeah,
cube.
yeah, 2.
Plus here we will be getting, here we got n by 2, right? Now we will be getting here as n by 4, right? Where n value, here n by 4 is the value, t of n by 4. We will be getting here n by 4 plus 3 by 2 plus 1 of n. So this is one value. So if I substitute this into this, we will be getting 3 cube to t to the power of t of n by 8 plus, okay, 3 square. This is 3 square by 4 plus 3 by 2 plus 1 of n. From this, if I take n as common, what is the value we are going to get from this part? This is 3 by 2 whole square. We can write this like this, right? 3 square by n by 4, we can write this in the form of 3 by 2 whole square, right? This part.
Yeah.
Plus 3 by 2 plus 1 of n.
Geometric progression. The common ratio being
Yes.
3 by 2.
Similarly, what is the next value we are going to get here? 3 by 2 whole cube, right?
Cube, yeah.
Like this, we are going to get these values. Okay, until 3 of log n.
Log n.
Log n.
So it's a finite sequence.
Plus here we have to get this 3 by 2 for log n minus 1. This is a log n value. This is n minus 1. Okay. If this part is clear for you?
Yes, sir.
So from this we can, as you all know this, if a power log n, we can write this as n power log a, right? This part.
Yes, sir.
So we can write this 3 power log n as into the power of log 3, right? So from this, what is you all know this log 3 value, right? We can compute this log 3 value in any
With
calculator
base 2,
and
sir,
get
with
this value.
base 2. With base 2,
Yes,
because we are doing
yes,
binary.
yes.
Yeah, that is that
Base 2.
probably that 1.5 number that you wrote to the bar.
Yes. Like this, we will be getting this order of n power 1.59 roughly. Okay.
Yeah.
This is the time complexity. So we have reduced this from n squared to order of n to the power of 1.59, right? Like this, we have reduced this. So as a given question is very simple question, but the logic is very difficult, right? But if you are able to understand this logic, it is very easy for you. Only thing we have done is we are going to compute here AC, BD, and AD plus BC values, right? These are the only thing we are going to compute. In our logic, we are going to use this only once, but the recursively on the backside it will be calculating the solution part, right?
Yes, sir.
Let us go to the code. Okay, this is the code part, right? Okay, here you can see the, if it's a single, if here now you are able to understand this logic. It is easy for you now. Okay, let me take this. Okay, here it is a function call which is made on this, and if it is a single digit, this is for checking the whether the digit is single or not. If it is a single digit, we directly compute the x into y value. If it is not a single digit, we are going to calculate and assign this x and y values. So to perform this x into y, what are the values we need? We need this value of a, we need b, c, and some values are required for that, right?
Yes, sir.
Okay. So here where 1 means a plus b, okay, and here where 2 means, I am explaining you roughly, later I will explain you brief. Here c plus d, where this is where 1, 2, c plus d, and where 3 is ac, where d is bd, and where 5 is this length by 2. Okay, we are going to compute, these are the values which we are computing in this Katsuo algorithm, right? Previously,
Yes.
these are the values which we have computed while performing this recursive approaches. So this AC part, this BD part, and C plus D and A plus D. As you all know, why we are computing these values, right? A plus B and C plus D.
Yes, sir.
Because to get the value of AD plus BC, we are computing these values also. So these are the values we need to return. So for returning these values, we need to write a function for that, right? Okay. Later, this is a result part. This is given in the reverse order. This var 3. What is this var 3? AC, right? This is var 3. This is 4. Okay. Kindly answer me. What is the var 3 here?
AC.
AC, right? AC into, this is 10 to the power of 2 into var, right? 10 to the
Yeah.
power of 2 into, what is the var part here?
Bar
What is
5
the
is n by 2. Bar 5
n by
is
2.
yeah.
So 1 by 2 means it is n, right?
Yeah. Makes sense now.
Plus here AD plus, you can see here AD plus BC, this AD plus BC part. So what is the AD plus BC value? We need to compute it. Okay, here it is they have already computed here. Okay, AD plus BC, they have var 1 plus var 2.
Yeah,
What is the var 1? A plus B.
Yes,
Now
sir.
you understand the logic, right?
Yes, sir.
Yeah. Now it all makes sense.
Okay, now all the dots are connected now. Okay, here it is A plus B and it is B plus C, and that's why only we are computing this before. Our in this code, our aim is to find these variables. Okay, what is A, what is B, what is C? We need to find them only. Okay. This is our task. This is a very simple task, right?
Yes, sir.
Yes, sir.
All our task is only to find this a value, b we need to only find this a, b, c, d, and later we can return them a plus b, c plus d, a, c, b, d, and the length
Just
of
one
this.
equation for the third term and the
Yes,
final calculation.
yes, this is okay. Is it clear? This part,
Yes,
this
sir.
entire coding part. Okay then.
Now I think we can handle it in OPP. It's looked very difficult.
Yes, this is it's okay. We can handle.
Yeah.
Okay, actually, you all might think that this is a different algorithm. What is this algorithm? You might think like that, right?
So the moral of the
Request.
story is,
Let us move to this.
however
I have already.
complicated the algorithm is, if it is can be expressed in a recursive form, you just need to know how to take a complex case, divide it, make it a simpler case, and do a recursive call. That's it.
Yes.
So that is one part, and when the result comes back, it should be arranged in the proper sequence. So that
Yes.
arrangement is that line 19, right? So divide and conquer. We're dividing it, conquering it in
Yes.
that Karatsuba, and that organizing it properly is line 19, which is that 10 to the power or whatever, right? That is actually the similar to merge set, right? You split, and then when you are merging it together,
Yes. Yes.
you get it organized. So
So
that is that line.
every time we are going to return this Karatsuba, right? So every
Right.
time we are returning, the value will be taken by some other variable. Okay. Here we
Yeah.
are printing it. Okay. As it is returning, we need to we also keep track of that return variable also, right? So it is simply a recursive value. It keep on recursively it keep on divides them and conquers the solutions one by one. Okay. That's why we call them as divide and conquer approaches.
Yeah.
Here this is a simple solution. You can see it is a 10-line solution, I think.
Yeah.
Okay. Here in the first step, to compute the to know the length of this integer, right? This is an integer, right? Only one integer. So how do we find the length of this integer? By converting it into a string, and we are going to compute the length of this integer, right? This part clear? This length part.
Yes, sir. Yes, sir.
Yeah, this
So
part
after
is
computing of this yes.
now clear, sir, because you are taking bigger or smaller, we don't know. So we take that whatever is a bigger, that is our n.
Oh yes, that's part only we are going to take it as length from the given to one.
Because you can take a
So
5-digit number and a 3-digit number, so you want n to be 5.
yes. So as you have previously, as we have talked that for taking the length of this, we are going to take a local variables, right? So every time this Karatsuba function is called, in this function only we are going to call this calculate design function, right? So every time we are going to take a new A, B, C, D and n values. Okay, do you get this?
Yes, sir.
So
And it will return. Yeah. So in the stack, the
yes,
control will flow, and you'll get the new number, and then you can rearrange,
yes,
and yeah, makes
yes.
sense.
Every time we are going to create a new local space. Okay.
Yeah.
So here before computing this AD plus BC Karatsuba function, we need to compute this AC plus BD, right? AC into BD, A into C and B into D part. This part should be computed before computing this AD plus BC because we are going to use this AC and BD in this function part. So we have computed this AC BD in the calculate design part only because the implementation is not given in this function. It is a suffix code, right? Prefix code it is given like this.
Yes, sir.
So we should implement this. The only thing we need is we need to pass. It is like simply multiplication. Instead of Karatsuba, replace this as multiply. It's simple, right? Multiply num1 into num2.
Yes, sir.
Okay then.
This
Here,
is actually very interesting. So Karatsuba is a kind of function which is being called inside calculate assign, and calculate assign is also calling Karatsuba. So essentially,
yes,
these are like
this
yeah,
is a recursive equations only. These are
yeah,
we have different types of recursions, right? A function
yeah,
calling itself and a function calling other function. Another function is calling the same function.
yeah, but with a different smaller parameter, or like in this case, original xy was, let's say, length of 6. So we are calling it two things. We are actually doing calculate assign on the line
Yes.
17, and then on line 18 we are calling it with a smaller like that n by 2. But calculate assign when it takes the xy, it is actually calling Karatsuba with num1 and num2, which is actually again 1 digit less.
Yes, every time the local copies are created for that function, right?
Right.
So actually, for our understanding purpose, it will be some complex, but the compiler knows the local values of that function, right?
Yeah.
So it is
Yeah.
going to use the local values only.
Yeah. The stack variables within the stack.
So
I mean the area of the
yes.
memory. Yeah. Right.
So here, how we find as I have told you, we need to find this a value. Sorry for this, a b c d values only here. So how we find this a value? By simply, this is a integer x which is given, right? By dividing this integer x, it is l, okay, which is n by 2. This is half, okay. For the in the previous example, it was 3, right? 10 to the power of 3, which is n by 2. As the previously we have taken an example of an integer of length 6.
Yes, sir.
So we got L value as 3 over there. So like this, we are going to take A value by integer division of this 10 to the power of L, and the remainder part will be the B value, right? So only these two lines are repeated. If you are able to find the values of A and B, it is simple for us to find this C and D also, right?
Yes, sir.
This is
Yeah, it is
because
simple, but just we have to think of
yes,
it. We have to just dry run with a few examples.
yes. After computing of this, keep in mind that here it is given only the Karatsuba function for this AD plus BC. If you know the logic, it is very clear for you. If you don't know the logic, only this function is called here only. You don't know that you need to call this function before to compare this AC and BD, right? If you know the logic, you can directly call this over here and you can compute this AC and BD values. If you don't know that, you can't able to do this function part, right? Even though you are able to find this A, B, C, D values, you can't able to find this function part, right? You don't know that you should use a function in this calculate and design part, calculate and assign part. Okay. Okay. Is this implementation clear for everyone?
Yeah.
Yes, sir.
Okay then. As I have not run it, let us run this. Okay, you can see this public cases are all passed. Let us check for the private cases. Okay, then this 5 out of 5 private cases are also passed. Okay, are there any doubts for this today's session?
I think so that explanation helped. Otherwise, the code is actually very simple once you know the logic.
Yes. If you don't know the logic, the code might be very complex that you might not understand ever, right?
Yeah.
Yes, what is happening, we won't get an idea what is going on inside.
Yeah. So
Now with
the
this
function,
equation dividing into 3, we are dividing the number
Yes.
into half. One part is
Yes.
A, one part is B.
Yes.
so far we had learned recursion like A calling A with a smaller set or whatever, right? Or the sorting, merge sort, whatever, right? This is actually function. Let's say K calling C and C calling K, right? So it's like that. So
Okay.
yeah, that's very
Yes,
interesting.
yes, like that. Even though now, if this Karatsuba function is not given, also you can able to do now, right?
Now, yeah. I mean, yeah, a little bit of practice, yes, should be because we can derive that line 6 actually, right? Because that's the only part.
Yeah.
Because
Yes. Only now, you if this Karatsuba function is not given, you can instead of taking this var1, var2 and calling this function, you can directly implement that lines of code over here only, right?
yeah,
In this
yeah,
function part only.
yeah.
As I have tried in different approaches. Okay, for explanation sake, for this part I have taken in different approaches. Here, this is also similarly like that only. Okay, no need that. Okay. Okay then. Thank you everyone. Are there
Thank
any
you.
other doubts for this?
Sir, I had a doubt in a binary search tree, the deletion part, right?
In binary search tree, yes,
Yeah, deletion function is there, right? In that class definition.
yes. The
I'm not
class.
understanding.
Okay.
Yes, the deletion part I'm not getting.
In the binary search tree, are you regarding the code or regarding the explanation of
Yeah, the code part.
the code part? Okay. In binary search tree, okay. Search tree, right? So
Yes, sir. Week 6.
in binary search tree, if you are going to delete this leaf part, so we need to mention some conditions. Okay, the if the deleting element is a leaf element, leaf one, we don't need any operations. Okay, and how do we check the given node is a leaf node or not? We simply check the left and right. If the left is none, and if right is none, then simply it is a leaf node, right?
Yes, sir.
Okay, if so, we can directly remove this part. We can directly make the node as none. Okay, that node.
Yeah, leaf is fine.
So this for leaf we can do like this. And if it is not a leaf, if it if it is not a leaf, and now I'm going to delete this node. Okay, this internal node. So to delete this internal node, first we need to check similar to the leaf only. If left equals to none or right equals to none, we need to check this. If one of them is none, if this is none and this is not none, in this case, okay, so one of them is not none. So what we should do, we should replace this node with the child node. Okay, this node should be replaced with this. Okay,
I didn't get, sir. Just
okay,
repeat.
you should replace this internal node with this child node. Okay, this node will be replaced at this position. Okay,
Okay, if the not the child
node
one,
has only
top one
single
is
child.
removed. Okay, okay. You're
If there is only
replacing
single
the
child.
child one.
Okay, so if this is also not the condition, and if the internal node has two children, okay,
Okay.
now if it has two children, okay, this part is greater than this in this node, right? These are the greater values, these are the lesser values. So now if I'm going to delete this part, what we should check whether the left is none or not and the right is none or not. We should check this part. Okay, we should
Yes.
check. And if, as we have already checked this both none case and one of them none case, and now we should check. Okay, we should come in this order. Okay, it will be helpful. First of all, you should check for if left not equals to none and right not equals to none. If this is the case, it is an internal node having two children, right?
Yes.
So we need to replace this with the left side smaller element or right side, okay, right side smaller element or left side greater element. Okay, in order successor or in order,
Just to replace.
yes. For example, if we have a tree like this, there are no, okay, if this is 6, if there is a 5, and this side we have 8, 7, sorry, we, and here we have 7, we have 9. So if I'm deleting this 6, okay, and this 6 has this both left and right shells, right?
Yes.
So if you are going to delete this 7, we should replace this with this in order successor or this, okay, in order predecessor. Okay,
Okay. How to
so
know which to
here,
replace?
so you can apply any one of the approaches in your code. You don't need to apply this both approaches. Okay,
Okay,
you
sir.
can replace with this element or this element. Okay,
Okay.
you don't need to apply this both approaches. Okay, any one of the approaches is enough. So if you're trying to do this, apply this part, so only thing is you keep this node in some other node temporary node, and you make this inside this node and make this node as a none one, or before making this as none, you check whether this node has any left or right children. As okay, let me explain you. As we are going to traverse towards the right, okay. If you are going to check for the last this part, what do you call this part?
Child node.
Yes. For if we are going to delete this part, this is called in order successor, in order predecessor.
In order predecessor.
Yes. So we need to traverse for the in order predecessor. How we are going to get this in order predecessor? We are going to first traverse for the left, and later we are go towards the right of this right of every child, right? Until we reach the leaf node.
Yes.
First, we are going to go towards the left, and later we are going to go towards the right until we reach the leaf node. Okay. If this has two nodes and this has two nodes, okay. So what is the in order predecessor here? This is the in order predecessor we got here, right?
Okay, so we check the extreme left, then we check the extreme right.
So first left, and we are going to go to the extreme right, okay, until we
Yes.
reach the leaf node.
Okay, sir.
So
That's
after reaching this leaf node, as this is a leaf node, we can directly remove this, right? But we need to store this value because we should replace this with the root node, root or this any internal node we are going to delete. So we are going to replace, take it, make it okay, keep it in a temporary variable, and you can do any other operations you know, and later make it as none and replace this with this root node, okay.
and finally we will delete it from the bottom.
Yes. So if you have a doubt, right? If there is a doubt, if you don't have this part, okay, if you don't have this element, now you are going to delete, okay. Here we have 3 and here we have 2, for example say. So what is the element you are going to delete here? We have come to the extreme point, right? This is the
Yes.
extreme value we got here, this 3.
Yes.
To the extreme right we got this 3. So we need to check for the whether it is a leaf node or not, okay.
Yes, sir.
So here it is not the leaf node, but
So
here the leaf node is 2. We cannot replace this 2 here because 2 on 2's left side 3 will be there. What is the binary search tree condition? On the left side the value should be lower, and the right side the value should be greater than the root node, right?
Yes, sir.
So
So it cannot be replaced by this because it is not the in order predecessor now.
so we should exchange these values, and we should later we should change this root node, okay.
We're exchanging the values at the bottom.
Yes, first of all we need to change these values, right? We can change these values also, and later after changing these values we can change the root node value, okay. This will
Okay,
be clear
actually we
for
are
you
only
if you
deleting, if it is 3, we are only deleting 3. But we are bringing that to the bottom of the left.
yes, if
Then
you
we
make
will
this as
change the values and delete it.
if you make you can make this as 2, and you can make this root node as 3, right? So this will
Yes.
be clear. On the left side of 3 we have the smaller value. So if the if it is a leaf node, we can directly exchange it. If it has one child, we can replace them and again replace it. And if it is having 2 children, so we are going to the extreme, anyhow we are going to towards the extreme right point, we are going to go to the leaf node only, right?
Yes, sir.
So for this condition only you are going to mention change these values. So for this, in order you can write a different function, okay. In your code, if it is a leaf node you can directly remove it. If it is having one child, you can you can replace that with the child node, so that the data will not be lost. And last condition, if it has two children, okay, and at that point only you are going towards the in order predecessor or in order successor condition, right?
Yes. That,
So in that situation you can, if this is the case, you can call a function for that, okay, for like in order successor or in order predecessor, so that this function will compute the rest of the part of this. So in this function you can mention, if it is a leaf node, you can directly exchange this with the parent node, or if it is a like this, you can mention some conditions, okay, or you can directly make the steps over here only.
sir, in this delete function, actually they are finding a value v, right? So to delete a node v, right? Something like that.
Yes, if this binary search we can directly search right in order of n.
So this make
Best.
empty is like leaf node, and right one is the one explained, right? And the left one is
Yes.
the one if you have another left. Then one else part is
Yes.
there, right? So one else part is there, right? That
Yes.
self dot value, self dot left dot max val. What is that, sir?
Left dot max. Okay, can you show your code? What is the approach you have done?
So
You have gone through
the right that in GitHub nodes that algorithm is there, right?
in GitHub Notes.
Yes, sir.
Can you open that? Can so that I can explain you in brief?
1 minute, I'll share that, sir.
Okay then. Okay, let me stop the sharing. Again. Okay, I think for today's session, these are the contents we have discussed. So
I'll share.
I'm going to stop the sharing. Okay.
Is it visible?
Let me stop my. Yes, yes. For the delete, first of all, we are checking whether the root tree is empty or not. This is the first if condition in the 65th line.
Yes, sir.
If it is empty, we are directly returning it.
Yes.
So no need to delete. So for the second condition, as we have passed this v, right, we are going to delete this v value v, right?
Yes, sir.
For deleting, we are checking with the value whether the root value. Every time we are, what are the conditions we have? We have the for the left side we are going to have the smaller values. For the right side we are going to have the larger values.
This
And
is
if it is
actually
equal,
recursive, right? Like it is not
yes,
deleting anything, right?
it is not deleting it. We are again calling that function on the left
Function
side,
again.
left,
Yeah, again to go
and
to
we
the
are
left.
going, and
Yeah.
here we are moving to the right side. And if
Yes, this
if
is
the
what.
value equals to the v, we are going to perform some operations over here. Okay.
Yes, sir.
So if it is equals to v, here you can see we are going to check whether it is a empty leaf node or not. If it is a leaf, we are directly making it as empty. Okay. In this make empty function, we
Yes,
are
we're checking it
making.
empty and making is empty, as explained. Yeah.
Okay. Okay.
Yes,
Then
sir.
we are going to
Mm.
check whether it has a left node is empty or not. Okay. And if it is having the left node as empty, we are copying the right value. If the right value is also empty, the right value is none, right? So we are starting from
Right.
leaf node. In the first leaf node only, we are checking both none conditions. So if this both none is true, we are directly coming out of this if condition, right? After computing this if block, in the first
Yeah,
only we are
this one.
checking
If it
both.
is empty.
Okay, this is an like and operation of both. So if this and is not working, means one of them is not none, right? So that might be a left one, that might be a right one. If this fails, means the right one is
Yes.
not empty. So we are going to copy this part. So if this both conditions are fail, means it has two children, right? If this both left is empty and right is
Yes,
empty
yes,
is
yes,
failing, means
yes.
it is having two children. So we are going to do this part.
Yes, yes.
So you can see here we are again calling this
Yes, it is
delete
some
left
false.
max. Okay, is it clear, sir?
This part is not clear.
This maxwell function, go to the maxwell function. It is calling for a maxwell function, right? Yes,
Yes,
you
yes,
can.
sir. This one.
You can see here it is moving towards the right side. Okay, continuously moving for in order predecessor to find the in order predecessor. It is continuously moving towards the right side and later find replacing with that.
Okay.
Okay, it is going continue
Okay.
returning. It is returning here. It is not giving a void. Okay, we are going to replace this
Yes, it is moving
return
towards the
value.
right, that means first.
Yes, you
Okay.
can see.
If it have two children, it is moving first towards the right.
Yes, it's continuously returning here. Okay, returning and the self dot value will be replaced with the self dot value. We have to change the root this node value address part also, right?
Address.
So with the in the
The
self dot
value should
value,
go, Yeah.
Yes, in the self-dot value, we are just only changing the value part only, right?
Yes. Yes, we are changing only
You can
value.
see now in the below, it is returning here self dot left dot max value. It is returning over here. Now later after returning it, we need to delete the leaf node, right, which is replaced over there. This self dot left dot value, which is replaced, we should let me show. Okay, keep this in mind. After exchanging with the predecessor value, okay, this
Sir,
predecessor or successor
are you
value, we need
explaining
to,
something? I
yes.
don't know. Are you explaining something? No, right?
Am I audible?
Yes, sir. Yes, sir.
Okay,
I
this
thought
part
you
is, this part is
are.
clear. 81 and 82 are clear. Line number 81 and 82.
No, line 81, I am half clear that it is moving towards the right, but I don't
Okay,
know
here.
why it is self dot left dot Maxwell. It is already moving towards the right, right?
Okay, let me. Okay, this part I will be explaining you.
Yeah, just these two lines will
Is
be
my is my screen visible for you?
1 minute, sir. You should stop sharing.
Huh, my screen is not visible for you.
No, sir, it's not visible.
Okay, then I will take this. Okay, how can you? Okay, can you post this?
Just
Copy
take
this.
a screenshot of this window, and then you can explain it on your window. I'll stop sharing.
Yes, yes. Okay then. Okay, you can.
Okay, you can stop sharing.
I think I will stop this YouTube streaming. Okay. Oh, shit.